Some nights, the universe feels closer than usual, not because the stars move, at least not in any way our eyes can follow, but because something inside us grows quieter, more receptive, more willing to drift with the soft pulse of existence. Tonight is one of those nights. The kind of night when your breath aligns with something wider than the moment, and the gentle rhythm of life begins to echo the same slow cadence that has guided galaxies for billions of years. So allow yourself to settle in, letting the weight of the day uncoil from your shoulders as we step into the silent fabric of the cosmos together. The story doesn't begin with stars. It doesn't begin with planets or light or the swirling dust of nebulae. The truth is far softer, more delicate, like the first threads of a tapestry woven in absolute darkness. In the beginning, before anything had a name, before time itself knew in which direction to flow, the universe was nothing more than a whisper of possibility, a breath without lungs, a thought without a thinker, a faint trembling of potential suspended in an endless stillness. Scientists call it the quantum vacuum, but even that name feels too heavy for something so subtle, so almost non-existent. Maybe the universe began the way we drift towards sleep, not with an explosion, but with a gentle surrender. Then, in that silence, something shifted. Not violently, not suddenly, more like the soft ripple of a dream forming just beneath consciousness. A fluctuation so tiny that if you tried to capture it with equations alone, it would slip through the symbols like water through open fingers. Yet this delicate tremor carried within it everything that would someday become galaxies, oceans, trees, languages, hopes, and the quiet breath you are taking right now. It was a seed of becoming. As this first tremor unfolded, space stretched outward, not like a balloon inflating, but more like a quiet horizon slowly parting to reveal a land that had been waiting unseen. There were no stars yet, no radiant suns or spiraling arms of galaxies. Only a warm, dense glow, thick and uniform, as if the universe were wrapped in a soft cosmic fog. It was peaceful, incredibly peaceful, the way a deep sleep feels when you sink just below the surface of awareness. And from this early calm, temperature, pressure, and energy began to gather into patterns, tiny speckles in a vast glowing field. These speckles were not yet matter as we know it, but they held the rhythm of future creation. Some places were just a little warmer, a little denser, a little richer in the invisible hum of possibility. And those slight differences, so small you might think they would vanish, became the seeds from which every galaxy would grow. The universe is like that sometimes. The quietest imperfections shape the grandest destinies. As the cosmic fog thinned and cooled, the first atoms began to form. Hydrogen, humble and light, arrived like the universe's first breath. Helium followed, gentler still, glowing faintly in seas of expanding space. There were no planets yet, no moons or comets tracing frozen arcs. Only drifting clouds of gas, stretching across unimaginable distances. But even in this vast simplicity, the universe was already carrying within it an unspoken intention to create structures that could someday wonder about their own beginnings. Slowly, gravity, patient, steady, tireless, began to gather these luminous clouds. Not hurriedly. Gravity never rushes. It is the slow hand of time, drawing everything inward with an embrace so subtle you hardly feel it until you are already leaning into its pull. Hydrogen fell into hydrogen. Helium joined the gentle descent. And within these gathering clouds, the earliest stars began to awaken. As this first tremor unfolded, space stretched outward, not like a balloon inflating, but more like a quiet horizon slowly parting to reveal a land that had been waiting unseen. There were no stars yet, no radiant suns or spiraling arms of galaxies. Only a warm, dense glow, thick and uniform, as if the universe were wrapped in a soft cosmic fog. It was peaceful, incredibly peaceful, the way a deep sleep feels when you sink just below the surface of awareness. And from this early calm, temperature, pressure, and energy began to gather into patterns, tiny speckles in a vast glowing field. These speckles were not yet matter as we know it, but they held the rhythm of future creation. Some places were just a little warmer, a little denser, a little richer in the invisible hum of possibility. And those slight differences, so small you might think they would vanish, became the seeds from which every galaxy would grow. The universe is like that sometimes. The quietest imperfections shape the grandest destinies. As the cosmic fog thinned and cooled, the first atoms began to form. Hydrogen, humble and light, arrived like the universe's first breath. Helium followed, gentler still, glowing faintly in seas of expanding space. There were no planets yet, no moons or comets tracing frozen arcs. Only drifting clouds of gas, stretching across unimaginable distances. But even in this vast simplicity, the universe was already carrying within it an unspoken intention to create structures that could someday wonder about their own beginnings. Slowly, gravity, patient, steady, tireless, began to gather these luminous clouds. Not hurriedly. Gravity never rushes. It is the slow hand of time, drawing everything inward with an embrace so subtle you hardly feel it until you are already leaning into its pull. Hydrogen fell into hydrogen. Helium joined the gentle descent. And within these gathering clouds, the earliest stars began to awaken. Somewhere, in one of those nurseries, a small, unremarkable star was born. It was not large or fierce like the ancient giants that came before. It glowed steadily, modestly, with a warmth that invited planets to gather around it. In time, one of those planets cooled into a sphere of oceans and continents, wrapped in a thin, trembling veil of air. And on this world, something extraordinary happened. Chemistry learned to breathe. Life, fragile, curious, persistent, began not with intention but with rhythm. Molecules met, parted, and met again, dancing in the subtle warmth of shallow seas. Over time, they learned to store information, to copy themselves, to build shells and membranes, to harness energy from light. Life grew patiently, like the soft unfolding of a fern frond in early morning. And as it grew, the universe gained something entirely new, the ability to look back at itself. And now, here you are, one tiny spark in that long chain of cosmic becoming, breathing gently, listening to the quiet story of a universe that has been drifting toward this moment for 13.8 billion years. Your heartbeat echoes the fusion rhythm of ancient stars. Your bones carry atoms forged in the cores of suns older than memory. And your thoughts, those slow, drifting shapes of awareness, are made possible by the quiet unfolding of cosmic history. Tonight, as we float deeper into this silent tapestry, let the immense timescales soften your mind. Let the distances stretch out like a calm horizon. You don't need to hold anything tightly. Just breathe. The universe has been unfolding for billions of years. It can continue without your effort. All you need to do is rest and drift with the story, letting each image fade softly into the next, the way galaxies glide through the night without ever making a sound. As we drift deeper into the quiet expanse of cosmic history, imagine yourself gently floating beside the forming Milky Way, watching its spiral arms stretch outward as if reaching for something just beyond sight. There is no sound here. Space is vast and airless, a realm where silence is the natural language of existence. Yet despite the stillness, everything moves. Stars swirl in slow orbits, nebulae drift like delicate clouds, and dark matter forms an invisible skeleton holding the galaxy's shape. Nothing is truly still. Even in the calm, the universe is breathing. If you watch long enough, longer than a human life, longer than civilization itself, you begin to notice a rhythm. Galaxies rotate like ancient wheels, taking hundreds of millions of years for a single turn. Stars pulse and dim, some with steady cycles, others with chaotic flickers. Space itself stretches, creating more room for these motions to unfold. It's a gentle choreography, one so slow and vast that our minds can grasp it only by letting themselves loosen, sink, and float, the way your consciousness softens just before sleep. But the Milky Way was not always the elegant spiral you see in pictures. In its youth, it was turbulent, full of collisions, mergers, and chaotic clouds of gas swallowing one another. Whole clusters of stars drifted like migrating islands. Dark matter halos overlapped, tugging gravitational threads in unpredictable patterns. And yet, through all this chaotic motion, a kind of order gradually emerged. Gravity's gentle hand smoothed the turbulence, guiding matter into a graceful spiral. It's comforting to know that even the universe needed time to find its balance, that chaos slowly settled into harmony, that beauty was something shaped patiently, not instantly. Deep within one of the galaxy's forming arms, a cloud of dust and gas, cold, dark, and dense, began to collapse under its own weight. There was nothing exceptional about this cloud. It was neither the largest nor the brightest. It didn't glow with the dramatic colors of famous nebulae, but it held within it the seeds of something remarkable. As the cloud contracted, it fragmented into smaller pockets, each forming the beginnings of a star. Most would become ordinary suns, unremarkable in the grand catalogue of celestial bodies. Yet one fragment, spinning gently, cooling slowly, carried a particular balance of mass, momentum, and composition. This fragment would become our sun. Its early life was a quiet one. Before it blazed, before radiance filled its surroundings, the young sun was nothing more than a warm sphere hidden inside drifting dust. But deep in its core, hydrogen atoms were being pushed closer and closer, squeezed by gravity with relentless patience. Pressure grew, temperature rose, and then, in one silent, transformative moment, nuclear fusion began. It wasn't a violent ignition. It was like a steady flame blooming in darkness, a fire that would burn calmly for billions of years. The sun awakened, and its light swept through the surrounding disk of dust and rock. This disk, swirling like a flattened cloud, held all the materials that would eventually become planets. At first, it was a chaotic swirl of icy grains, pebbles, and drifting clumps of rock colliding in slow motion. In the silence of space, these collisions were soft, delicate, like snowflakes merging. Over millions of years, the clumps grew. Some shattered, some joined, until eventually, several large bodies began to take shape. Jupiter, vast and regal, Saturn with its shimmering rings to be, Uranus and Neptune drifting in the cold outskirts, and, of course, a rocky world warming close to the sun, our future Earth. Earth's early form was nothing like the tranquil planet you know. It was a sphere of molten rock glowing faintly beneath a sky of ash and vapor. Asteroids rained down continually in the heavy bombardment period, sometimes so large they would vaporize oceans and reshape continents before the continents even fully existed. But over time, Earth cooled. The crust solidified. Water condensed and fell as rain for centuries, filling basins and carving valleys. The planet was preparing a stage without yet knowing what would walk upon it. In the warm, shallow seas of early Earth, chemistry began its patient work. Molecules accumulated, combined, broke apart, and recombined. Lightning flashed across thick skies, volcanic vents bubbled minerals into the water, and ultraviolet light penetrated the upper layers of the ocean, triggering reactions that had never occurred before. Eventually, something extraordinary emerged, molecules that could copy themselves. They weren't alive, not in the way we understand life, but they held the spark of it. With each imperfect copy, new possibilities appeared. Life was not a sudden event, but a slow unfolding, a gentle tide that grew stronger with each passing epoch. As the first cells took shape, simple, single structures floating like microscopic bubbles, they learned to harvest energy. Some used sunlight, capturing photons in tiny molecular traps. Others consumed chemicals seeping from deep-sea vents. Over long, slow ages, they formed colonies, mats, and filaments. They released oxygen as waste, gradually filling the atmosphere with a gas that would one day allow fire to burn and lungs to breathe. The world changed, not through violence, but through countless small moments of persistence. Life built Earth the way threads build a tapestry, quietly, patiently, almost invisibly. When multicellular life finally appeared, the oceans transformed. Soft-bodied creatures drifted like underwater lanterns. Simple worms burrowed in the seafloor mud. Sponges filtered water with meditative slowness. And then, in a burst of evolutionary creativity, forms exploded in variety. Eyes emerged, sensing faint glimmers. Fins developed, pushing bodies through water. Exoskeletons hardened, providing armor and structure. The ocean became a stage filled with movement, color, and curiosity. And still, the universe waited. For billions of years, Earth remained just another planet in an ordinary corner of a galaxy that itself drifted in a vast cosmic web. Yet something profound was happening. Life was evolving toward complexity, toward awareness, toward a mind capable of looking up at the stars and wondering where it came from. The universe was weaving consciousness into its tapestry. Eventually, creatures crawled from the oceans onto land. Lush forests rose. Insects filled the air with shimmering wings, and massive reptiles ruled for ages. But even this era was temporary. The universe never holds on to any one chapter for too long. When the dinosaurs passed into memory, mammals grew and diversified. Forests became laboratories for new shapes and behaviors. Some creatures ran swiftly, others climbed. Some developed intricate social bonds. And within one lineage, a spark began to glow, an emerging ability to reason, imagine, and dream. Human beings were not inevitable. They were simply one possibility among countless branches of life's tree. But once consciousness awakened, the universe gained something new. You, your thoughts, your imagination, your ability to listen to this story and feel yourself drifting into the deep rhythm of cosmic time. Tonight, as you rest, remember that the atoms in your body were forged in stars that lived and died long before Earth existed. Your bones carry calcium formed in ancient supernovae. The iron in your blood was once at the heart of a massive star that collapsed in silence billions of years ago. You are a continuation of cosmic history, a temporary shape taken by the universe so it can observe itself with quiet curiosity. And as your breathing slows, picture the Milky Way drifting through space. Not quickly, not urgently, but with the serene motion of a great celestial river. Our sun orbits the galaxy once every 230 million years. In its entire lifetime, it will complete only 20 orbits. Space is vast, time is deep, and you are floating in the middle of it, safe and weightless, wrapped in the gentle hum of existence. Let the immensity soothe you. Let the distances dissolve your worries. In the cosmic scale, everything that troubles you becomes lighter, softer, easier to release. The universe is patient. It has waited billions of years for stars to form, for planets to cool, for life to awaken. It can wait a little longer while you rest. Observations of galactic rotation revealed something unexpected. The visible matter, stars, gas, and dust, was not sufficient to explain the speed at which galaxies turn. The outer regions of a galaxy rotate just as swiftly as the inner regions, defying the predictions of classical gravitational models. This discrepancy pointed to the existence of an unseen component, dark matter. Although invisible to telescopes, dark matter influences cosmic structures through its gravitational pull, forming halos that envelop galaxies and anchor them within the cosmic web. If one could visualize these halos, they would appear as vast, diffuse spheres extending far beyond the visible edges of galaxies. Their shapes guide how galaxies cluster, how they move, and how they evolve over billions of years. Without dark matter, galaxies would not hold together. Their stars would drift apart into intergalactic space. It is this unseen architecture that gives the universe its large-scale structure, arranging matter into filaments, sheets, and clusters that span hundreds of millions of light years. Within this immense network, cosmic voids stretch out as enormous bubbles nearly devoid of galaxies. These regions are not empty. Traces of gas and dark matter still exist, but they contain far fewer structures than the dense filaments surrounding them. Over time, gravity pulls matter from the voids toward the filaments, making the sparse regions even emptier and the dense regions increasingly populated. This redistribution shapes the evolving appearance of the universe as a whole. Zooming back into individual galaxies, more complexity unfolds. Some galaxies host supermassive black holes at their cores, objects millions or billions of times more massive than the Sun. These black holes shape the dynamics of their host galaxies. When material spirals into a black hole, it forms an accretion disk that can heat to extreme temperatures, emitting radiation powerful enough to outshine the entire galaxy. Jets of high-energy particles may shoot out from the poles, extending far into intergalactic space. These jets influence star formation, gas distribution, and the thermal state of galactic environments. Despite their reputation, black holes are not cosmic destroyers roaming through space. They remain where gravity anchors them and interact only with matter that comes sufficiently close. Around them, stars continue their orbits undisturbed, tracing paths that follow the curvature of spacetime. The physics near a black hole is extreme, yet the surrounding galaxy often appears serene from afar. In stellar nurseries scattered across spiral arms, new generations of stars constantly emerge. These regions are dense with gas and dust, illuminated by the radiation of nearby young stars. Over time, the intense light and stellar winds sculpt the surrounding clouds into pillars, cavities, and sweeping arcs. These shapes evolve slowly, testifying to the delicate interplay between gravity and radiation pressure. Some stars form in clusters, bound together by gravity for hundreds of millions of years. Others disperse quickly, populating the galactic disk as isolated stars. The chemical composition of each star reflects the environment in which it formed. Older stars contain fewer heavy elements, while younger stars, born after countless supernovae enriched the interstellar medium, have more diverse chemical signatures. In this way, stars carry within them a record of galactic history. Planets emerging around these stars also vary widely. Some orbit close to their parent stars, locked in scorching conditions with molten surfaces. Others reside in colder orbits, where atmospheres can freeze and oceans can solidify into ice. Some planets may possess deep atmospheres of hydrogen and helium, while rocky worlds carry traces of volcanic activity, magnetic fields, and seasonal cycles. The diversity of these planets expands with every discovery, challenging previous assumptions about how solar systems form and evolve. Large exoplanets that migrate inward from distant orbits can disrupt the formation of smaller worlds. Their passage can scatter debris, alter orbital paths, and reshape entire planetary systems. Yet in some cases, they stabilize their surroundings by clearing regions of gas and dust. The variety of possible outcomes reflects the sensitive dependence on initial conditions, a hallmark of cosmic evolution. On grander scales, galaxy collisions play a pivotal role in shaping the universe. When two galaxies approach, their gravitational pull distorts their shapes, drawing out long tidal tails of stars and gas. Over time, they may merge, forming a larger galaxy with a new morphology. These interactions can trigger bursts of star formation, as gas clouds collide and compress. The newly formed stars illuminate the remnant structure, revealing patterns of motion and distribution that encode the history of the merger. Beyond these active regions, faint streams of stars arc around galaxies, remnants of dwarf galaxies absorbed long ago. These stellar streams trace the invisible contours of dark matter halos and offer clues about how galaxies assemble over cosmic time. On even larger scales, galaxy clusters govern the dynamics of superclusters. They are bound together by gravity, yet drift within an expanding universe whose growth accelerates due to dark energy. This accelerating expansion means that galaxies outside a certain horizon will eventually recede faster than light can reach us, becoming forever unobservable. Over unimaginably long timescales, the observable universe will contract to only the galaxies gravitationally bound to one another. Despite this cosmic expansion, the small pocket of the universe inhabited by the Milky Way remains stable. The Andromeda Galaxy approaches the Milky Way at significant speed, drawn together by mutual gravitational attraction. Their future merger will reshape the night sky for any distant observers who might exist then, blending the two spiral galaxies into a massive elliptical system. Throughout all these phenomena, stellar birth, planetary formation, galactic evolution, cosmic expansion, runs a consistent theme. The universe changes through interactions spread across vast stretches of time. Structures grow from subtle fluctuations, evolve under the influence of gravity and energy, and eventually disperse or transform into new configurations. No single process dominates. Instead, countless mechanisms contribute to an ever-evolving cosmic landscape. As cosmic structures evolve, their interactions continue to shape the universe on scales far beyond what a single galaxy can reveal. Galaxy clusters, among the largest gravitationally bound objects in existence, contain hundreds or even thousands of galaxies orbiting within a shared halo of dark matter. These clusters are permeated by hot, ionized gas that fills the space between galaxies, emitting X-rays detectable by specialized observatories. This intracluster medium provides insights into the total mass of the cluster, including the dark matter that cannot be observed directly. Galaxy clusters themselves gather into even larger configurations, superclusters, connected by elongated filaments that span hundreds of millions of light years. These filaments, forming the backbone of the cosmic web, channel matter toward regions of higher density. At the intersections of these filaments lie the most massive structures in the universe, deep gravitational wells where galaxy clusters accumulate, merge, and evolve over billions of years. As matter flows along these filaments, smaller galaxy groups are drawn into larger clusters. These infalling galaxies experience tidal forces strong enough to distort their shapes. Some lose their gas as they travel through the hot intracluster medium. Others undergo bursts of star formation triggered by gravitational compression. Over time, repeated interactions gradually transform spiral galaxies into elliptical ones, altering their structure, star formation rates, and internal dynamics. Meanwhile, individual stars within galaxies follow their own long-term paths. Some stars drift into regions rich with gas and dust, where their radiation shapes the surrounding environment. Others travel into sparse, low-density areas, spending billions of years in relative isolation. Binary stars, pairs bound by gravity, can exchange mass, merge, or form exotic objects such as Type I supernova progenitors or neutron star pairs destined to collide. Neutron stars born from massive stellar collapse are incredibly dense, packing solar masses of matter into spheres just tens of kilometers across. When two neutron stars orbit each other, they emit gravitational waves, ripples in spacetime predicted by general relativity. These waves carry away energy, causing the stars to spiral inward until they eventually collide. Such collisions forge heavy elements like gold, platinum, and uranium, dispersing them into space. These elements, formed in rare but powerful events, later become part of planets, minerals, and even biological systems. At the same time, black holes formed from stellar collapse continue to interact with their surroundings. Some remain inactive, while others accrete gas from companion stars or interstellar clouds, generating energetic emissions observable across vast distances. Supermassive black holes at galactic centers regulate star formation by heating or expelling gas, preventing excessive buildup and maintaining long-term stability within their host galaxies. While these processes unfold on immense scales, smaller systems, planetary systems, orbiting stars, undergo their own transformations. Dust disks thin out, planets migrate, moons form or break apart, and atmospheres evolve through chemical reactions, stellar radiation, volcanic activity, and impacts. Some planets retain magnetic fields that shield them from high-energy particles. Others lose their atmospheres to stellar winds. Water may condense into oceans on some worlds, freeze into glaciers on others, or never form at all. Every planetary system represents a unique combination of conditions. Its star's properties, the composition of its protoplanetary disk, the dynamics of early collisions, and the long-term influence of gravitational interactions. These variables produce environments ranging from gas giants with powerful storms to rocky worlds with complex geology. Among them may exist planets with stable temperatures, protective magnetic fields, and atmospheres capable of supporting chemical cycles associated with life. Elsewhere in the universe, colossal structures evolve across scales that dwarf individual galaxies. Shock waves propagate through galaxy clusters when massive subclusters collide. These shocks accelerate particles to near-light speed, creating diffuse radio emissions. Meanwhile, quantum fluctuations imprinted in the earliest moments of the universe continue to influence the large-scale distribution of matter, connecting the smallest known scales of physics with the largest cosmic patterns. Observations from telescopes across the electromagnetic spectrum, radio, infrared, optical, ultraviolet, X-ray, and gamma ray, reveal different layers of this complexity. Radio waves highlight cold gas and synchrotron emissions from cosmic jets. Infrared observations peer through dust to reveal forming stars. Optical telescopes map stellar populations. Ultraviolet instruments trace hot young stars. X-ray observatories uncover black holes and the hot gas in clusters. Gamma-ray detectors capture the most energetic events in the universe. Together, these multi-wavelength observations create a composite understanding of cosmic evolution, each band revealing a piece of the puzzle. Combined with gravitational wave observatories and neutrino detectors, astronomy increasingly functions as a multi-messenger discipline, opening windows into processes once hidden from view. Yet despite these advancements, many mysteries remain. The nature of dark matter is still unknown. The cause of cosmic acceleration, attributed to dark energy, remains one of the central unsolved questions in cosmology. The behavior of space-time near singularities, the conditions of the universe in its earliest fractions of a second, and the possibility of other universes or dimensions remain open topics of investigation. The deeper the universe is studied, the more interconnected its systems appear. Structures arise from subtle initial variations. Forces act across enormous distances. Events occurring in one region influence others millions of years later. The history of the cosmos is a continuous chain of transformations driven by fundamental laws, yet shaped by countless interactions. As the universe continues to expand, the relationship between matter, energy, and space-time grows increasingly intricate. Even regions that seem empty at first glance contain fluctuating quantum fields, subtle vibrations that contribute to the overall dynamics of reality. These quantum fluctuations, present everywhere, play a foundational role in the evolution of the cosmos. They provided the seeds for the first concentrations of matter, which eventually grew into galaxies, filaments, and clusters. In the early universe, tiny variations in density, differences far smaller than anything detectable by human senses, were amplified by gravity over billions of years. Slightly denser regions attracted more matter, gradually becoming the birthplaces of galaxies. Slightly less dense areas became voids, expanding faster and draining material toward the filaments. This divergence created the cosmic landscape observed today, a vast network of structures connected by invisible gravitational threads. Spacetime itself acts as a dynamic medium, shaped by the mass and energy it contains. Massive objects curve spacetime, altering the trajectories of nearby particles and light. This curvature explains phenomena once considered mysterious: the bending of starlight near the Sun, the precise orbits of Mercury, and the dilation of time near massive bodies. Over cosmic distances, these distortions accumulate, influencing the paths of galaxies and the growth of cosmic structures. In regions of intense gravity, such as near black holes, spacetime curvature becomes extreme. Light emitted near the event horizon escapes only with significant redshift, losing energy as it climbs away from the gravitational well. Closer still, even the paths of photons are bent into orbits, forming a bright ring around the shadow of the black hole. These features, predicted by general relativity, were confirmed by direct imaging of supermassive black holes in distant galaxies. The material surrounding black holes behaves with remarkable complexity. Gas spiraling inward forms a turbulent, rotating disk. Friction and magnetic effects heat this disk to temperatures high enough to emit X-rays and gamma rays. Strong magnetic fields can channel some of this material into narrow jets that extend for thousands of light years. These jets influence star formation across entire galaxies by distributing energy into the interstellar medium. Beyond individual galaxies, the large-scale structure of the universe reflects a competition between gravitational attraction and cosmic expansion. Gravity draws matter together, forming clusters and filaments. Dark energy drives expansion, pushing structures apart over vast distances. The balance between these two influences determines the ultimate fate of the cosmos. Observations reveal that dark energy dominates, causing expansion to accelerate. This acceleration means that distant galaxies recede more rapidly over time. Eventually, many will cross a cosmological horizon, moving beyond the reach of any future observation. Even though their light once filled the night sky, their later emissions will never arrive. This gradual disappearance reshapes the observable universe, leaving only gravitationally bound systems behind. Within these bound systems, stars continue their individual life cycles. Small stars burn slowly, consuming their fuel over trillions of years. Larger stars evolve more quickly, expanding into red giants before shedding their outer layers. The remaining cores become white dwarfs, dense, cooling remnants whose glow fades over immense timescales. Stars more massive than about 8 times the Sun undergo far more dramatic endings, collapsing into neutron stars or black holes and dispersing heavy elements that enrich future generations of stars and planets. White dwarfs gradually radiate away their stored heat. Over spans of time so long they exceed current cosmic history, they cool into black dwarfs, dark, cold remnants that no longer emit significant light. Neutron stars maintain their intense magnetic fields as they rotate, emitting beams of radiation from their poles. These pulsars act as precise cosmic clocks, marking the passage of time with extraordinary accuracy. Meanwhile, the remnants of stellar explosions continue to expand, interacting with the interstellar medium. Shock waves compress nearby gas, triggering the formation of new stars. This feedback loop ensures that star formation persists for billions of years, although eventually the supply of cold gas diminishes. As galaxies age, they transition from active star-forming systems to quieter ones dominated by older stellar populations. In some galaxies, interactions and mergers rejuvenate these processes. When a gas-rich galaxy collides with another, their combined gas may ignite new waves of star formation. These events create luminous regions filled with young, massive stars. Over time, however, even these bursts decline as the available gas is consumed or heated, leaving behind long-lived stars that shape the galaxy's appearance for future epochs. Across the universe, the interplay of these processes produces a vast spectrum of environments, from intensely active starburst galaxies to tranquil ellipticals, where star formation has almost ceased. Each environment reflects a unique history shaped by initial conditions, interactions, mergers, and the surrounding cosmic landscape. Despite the differences, all galaxies and their components share a connection. They emerge from the same primordial fluctuations, evolved under the same physical laws, and contribute to the ongoing tapestry of cosmic structure. Their histories intertwine across space and time, forming a coherent narrative of growth, transformation, and complexity. As time stretches onward, the universe continues to reveal structures and processes that are not immediately visible on human timescales. Gravitational interactions, cosmic feedback mechanisms, and the slow drift of matter across intergalactic space build upon one another, shaping the long-term evolution of galaxies and clusters. These changes, subtle at first glance, accumulate into grand transformations across billions of years. In the outskirts of galaxies, faint streams of stars trace delicate arcs around their hosts. These streams originate from smaller satellite galaxies drawn too close to the tidal forces of larger systems. As a satellite galaxy or dense star cluster passes near the core of a more massive galaxy, gravitational forces stretch it along its orbit, stripping away stars and dispersing them along extended trails. These stellar streams preserve the orbital history of their progenitors, functioning as fossil records of past interactions. By mapping these streams, astronomers can infer the shape and distribution of dark matter within galaxies. Since dark matter governs the gravitational field, its unseen mass influences the curvature and direction of each stream. In this way, stellar debris becomes a tracer of invisible structures, revealing where dark matter halos are more dense, more elongated, or more clumpy than previously believed. Beyond the boundaries of galaxies, intergalactic gas plays a significant role in cosmic evolution. Although far thinner than any atmosphere found on planets, this gas forms vast reservoirs that connect galaxies through filaments of hydrogen and helium. Over time, gravity draws this gas toward galaxies, providing fuel for new generations of stars. Conversely, energetic events, such as supernova explosions or active galactic nuclei, heat and expel gas back into intergalactic space. This push and pull of matter creates a cycle of inflow and outflow that regulates how galaxies grow. In some regions, massive shock waves propagate through galaxy clusters. These shocks travel at thousands of kilometers per second and heat the surrounding gas to temperatures of tens of millions of degrees. Observations reveal these shocks as subtle edges or arcs within X-ray images of clusters. They indicate past collisions or interactions between subclusters, mapping the dynamic history of these enormous structures. Amid this activity, cosmic rays, high-energy particles accelerated by supernova remnants or jets from active galaxies travel across interstellar and intergalactic space. When they interact with magnetic fields, they produce synchrotron radiation detectable in radio wavelengths. Observing this radiation reveals the structure of magnetic fields that permeate galaxies and clusters. Despite their low density, these magnetic fields influence the behavior of charged particles, shape cosmic rays, and affect the motion of ionized gas. Magnetic phenomena also appear within individual galaxies. Spiral galaxies exhibit large-scale magnetic patterns aligned with their rotating arms. These fields arise through dynamo processes, mechanisms in which the motion of conductive gas amplifies weak initial magnetic seeds. Over time, these fields grow into coherent structures extending thousands of light years. Though subtle compared to gravitational forces, they contribute to star formation, gas dynamics, and the stability of galactic disks. On the scale of solar systems, magnetic effects play critical roles. Stars generate magnetic fields through rotating plasma in their interiors. These fields guide stellar winds, influence planetary atmospheres, and create cycles of activity such as sunspots and flares. Large flares release bursts of X-rays and charged particles that can reshape the chemical composition of planetary atmospheres or strip them away entirely. Planets with strong magnetic fields, such as Earth, develop magnetospheres, protective bubbles that deflect charged particles from the solar wind. Without such protection, atmospheric erosion can occur, as seen on Mars, which lost much of its atmosphere after its internal dynamo weakened. The presence or absence of magnetic shielding can determine whether a planet retains conditions suitable for liquid water. Within gas giants, magnetic fields can be even more intense. Jupiter's magnetosphere is so large that it extends beyond the orbit of some of its moons. Charged particles trapped within this field produce auroras more powerful than any seen on Earth. These auroras, detected through ultraviolet observations, offer insight into the interactions between Jupiter's magnetic field, its atmosphere, and the material emitted by its volcanic moon Io. Meanwhile, smaller rocky worlds undergo their own transformations. Tidal forces shape the geology of moons orbiting massive planets. Io experiences intense volcanic activity as Jupiter's gravity flexes its interior. Europa and Enceladus may harbor subsurface oceans kept warm by tidal heating. Ganymede possesses a magnetic field of its own, unique among moons in the solar system. Each of these environments demonstrates how gravitational and magnetic interactions influence planetary evolution. Across interstellar space, molecules form in cold regions where temperatures drop to just a few degrees above absolute zero. These molecules, ranging from simple hydrogen gas to complex organic compounds, adhere to dust grains, react under cosmic radiation, and eventually play roles in forming new stars and planets. Chemical processes in these clouds contribute to the diversity of matter found in developing planetary systems, potentially influencing the emergence of biologically relevant molecules. As stars move through the galaxy, they interact with these molecular clouds, triggering new waves of star formation. Massive stars emit powerful ultraviolet radiation that carves cavities into surrounding gas. Their stellar winds push material outward, while their eventual supernova explosions compress the surrounding regions, causing additional collapses. In this way, one generation of stars sets the stage for the next, forming a chain of events that continues across cosmic epochs. The life cycles of stars are tightly connected to the chemical evolution of galaxies. Early generations of stars contained only primordial hydrogen and helium. Through nuclear reactions, they created heavier elements and dispersed them when they ended their lives. Subsequent generations incorporated these elements, enabling the formation of rocky planets and the complex chemistry that eventually allows for biological systems. Thus, the periodic table can be viewed as a historical document, a record of processes carried out by stars over billions of years. Even beyond the visible universe, theoretical models explore possibilities for additional dimensions, cosmic inflation, and the quantum structure of spacetime. These concepts seek to explain phenomena not fully described by current laws, including the nature of dark energy, the behavior of the earliest universe, and the potential links between gravity and quantum mechanics. While these ideas remain speculative, they guide experiments and observations that may eventually reveal deeper layers of cosmic reality. As the universe ages, long-term processes begin to dominate its evolution, particularly those involving the cooling and dispersal of energy. Stars gradually exhaust their nuclear fuel, galaxies shift from vibrant regions of star formation to quieter collections of older stars, and intergalactic gas loses heat as it expands into larger volumes. These shifts are subtle on human timescales, but profound across cosmic epochs. In mature galaxies, the interstellar medium becomes increasingly enriched with heavy elements produced by multiple generations of stars. Dust grains composed of carbon, silicon, oxygen, and iron accumulate in dense clouds, influencing the thermal balance and chemistry of these regions. Dust scatters and absorbs light, obscuring some parts of galaxies while revealing others through infrared observations. Its presence affects how gas collapses to form new stars, often promoting cooling and increasing the likelihood of fragmentation. Meanwhile, as galaxies interact gravitationally, their shapes evolve. Spiral galaxies can develop bars, linear structures of stars and gas extending from their cores. Bars facilitate the flow of material toward the central regions, where it may feed the supermassive black hole or trigger central starbursts. Over time, interactions with other galaxies may transform spirals into lenticular or elliptical systems, each with distinct distributions of stars and gas. At the cluster scale, the motion of galaxies through the intracluster medium generates observable effects. As a galaxy moves through the hot, diffuse plasma, it experiences ram pressure stripping, a process that removes gas from its disk. This removal suppresses star formation and leaves behind streams of gas that may reignite star formation under the right conditions. These interactions contribute to the diversity of galaxy morphologies observed in clusters. Cosmic filaments, though extremely low in density compared to galaxies, transport matter and energy across enormous distances. Gas within these filaments gradually flows toward nodes where galaxy clusters reside. Over billions of years, this inflow contributes to the growth of massive structures. At the same time, the expansion of the universe stretches filaments, thinning them and altering their composition. Some simulations suggest that filaments may eventually fragment or disperse as dark energy accelerates expansion. In the realm of high-energy astrophysics, gamma-ray bursts stand among the most energetic events in the universe. These brief flashes originate from massive stellar collapses or the mergers of neutron stars. Their intense radiation can illuminate distant regions of the universe, revealing intervening gas clouds and the conditions of the early cosmos. Although short-lived, these bursts provide valuable insight into the life cycles of massive stars and the formation of heavy elements. Neutrinos, lightweight particles that rarely interact with matter, also play a role in cosmic phenomena. Emitted in vast quantities during supernova explosions, neutrinos escape almost immediately due to their minimal interaction with surrounding material. Detecting these particles allows scientists to probe the internal processes of dying stars that cannot be observed directly through electromagnetic radiation. Neutrinos from distant cosmic events carry information across immense distances, passing unhindered through galaxies, clusters, and cosmic voids. Gravitational waves add another layer to this observational landscape. Generated by accelerating masses, especially compact systems like binary black holes or neutron stars, these ripples in space-time travel at the speed of light. When detected on Earth, they reveal details about their sources that would otherwise be hidden. The combination of gravitational wave astronomy and traditional electromagnetic observations has opened a new window on cosmic evolution, enabling multidimensional studies of the universe. Across planetary systems, smaller-scale interactions continue as well. Asteroids collide, forming craters or breaking into fragments. Comets transport volatile materials from icy reservoirs, releasing gases and dust as they pass near their stars. These processes, while minute compared to galactic dynamics, influence planetary atmospheres, surface compositions, and long-term habitability. The solar system itself is an example of how local events shape planetary environments over billions of years. Within atmospheres of rocky planets, chemical cycles unfold under the influence of sunlight, volcanic activity, and interactions with the planetary surface. Carbon dioxide, nitrogen, oxygen, methane, and water vapor participate in complex exchanges that regulate temperature, pressure, and climate stability. These cycles depend on geological activity, magnetic shielding, orbital parameters, and the nature of the host star. Variations in any of these factors can result in dramatically different planetary climates. On some worlds, geological processes create continents, oceans, mountains, and shifting tectonic plates. On others, the crust remains static, producing landscapes dominated by vast plains or impact basins. Planetary interiors may contain molten layers that generate magnetic fields through convective motion. The thickness and composition of a planet's atmosphere determine whether liquid water can exist on its surface, a key factor for chemical complexity. The long-term evolution of planetary systems is shaped by stellar life cycles. As stars age, their luminosity changes. A star like the Sun gradually brightens over time, altering the habitable zone around it. Eventually, the Sun will expand into a red giant, engulfing nearby worlds and transforming the solar system's architecture. After shedding its outer layers and leaving behind a white dwarf, it will illuminate surviving planets with a faint, diminishing glow. In other star systems, the fate of planets varies widely. Some may be ejected from their systems by gravitational interactions, becoming rogue planets that drift through interstellar space. Others may spiral inward and be consumed by their stars. Still others may migrate outward, finding new equilibrium points in colder regions. The diversity of possible outcomes highlights the delicate balance governing planetary orbits. Across the cosmos, these individual stories accumulate into a larger narrative, one defined by continuous change, interconnected processes, and gradual transformations. Every structure, from dust grains to galaxy clusters, contributes to this intricate history. The universe evolves not through a single mechanism, but through countless interactions that shape its appearance across billions of years. As the universe progresses further into its long timeline, the processes that shape matter and energy continue to shift in subtle but significant ways. Stars that once illuminated their surroundings gradually transition into later stages of their evolution, leaving behind remnants that will persist for far longer than the luminous phases of their existence. These remnants, white dwarfs, neutron stars, and black holes, become the primary long-lived objects that populate galaxies as time extends into epochs far beyond the present. White dwarfs slowly cool as they radiate their residual heat into space. Without internal fusion reactions, their energy gradually diminishes, and their surfaces become colder over trillions of years. Eventually, they will reach a state where they emit little to no radiation, forming hypothetical black dwarfs, cold, dense remnants that persist in silence. Although none exist yet, since the universe is not old enough for white dwarfs to have cooled that far, they represent a future dominated by the remnants of once bright stars. Neutron stars, incredibly dense and compact, continue rotating for long periods, emitting beams of electromagnetic radiation when their magnetic axes are misaligned with their rotational axis. These pulsars act as precise cosmic beacons, their steady pulses functioning as natural clocks. Over immense timescales, neutron stars gradually slow their rotation, losing energy through magnetic braking. Still, their extreme density ensures they remain stable indefinitely unless perturbed by external forces or collisions. Black holes, formed from the collapse of massive stars or through galactic mergers, play long-term roles in cosmic evolution. Their gravitational influence persists as they capture nearby matter or merge with other black holes. Over exceedingly long spans, even black holes may not remain unchanged. According to theoretical predictions, they slowly lose mass through Hawking radiation, a phenomenon in which quantum processes near the event horizon create particle-antiparticle pairs, allowing black holes to emit tiny amounts of energy. Although this radiation is incredibly weak for large black holes, over unimaginable lengths of time, it gradually leads to their evaporation. Beyond individual remnants, the behavior of galaxies themselves continues to evolve. Star formation becomes less frequent as gas is consumed or heated by energetic processes. Without sufficient cold gas, galaxies transition from active, blue-hued systems filled with young stars to redder, quieter systems dominated by older stellar populations. Elliptical galaxies, already poor in cold gas, enter these phases quickly, while spirals like the Milky Way take longer to exhaust their reservoirs. Interactions between galaxies accelerate these transformations. As the Milky Way approaches the Andromeda Galaxy, their gravitational attraction will draw them closer, gradually distorting their shapes. Long before they merge, tidal forces will create streams of stars pulled from each galaxy. When the cores eventually collide, the central black holes may orbit one another in tightening spirals, emitting gravitational waves as they approach coalescence. The final merger will reshape both systems into a single, massive elliptical galaxy. Within galaxy clusters, similar processes occur on much larger scales. Clusters can merge, forming even more massive structures that reshape the distribution of dark matter, gas, and galaxies within them. The intracluster medium becomes further heated during these mergers, generating shock waves detectable in X-ray observations. Over trillions of years, as gas cools and star formation declines, clusters gradually fade, leaving behind vast populations of stellar remnants and wandering stars. Dark energy continues to influence the universe throughout this time. Its effect on expansion becomes increasingly dominant as matter becomes more diffuse. Eventually, galaxies not gravitationally bound to one another drift apart past the cosmological horizon, becoming permanently unobservable. Only local superclusters remain gravitationally intact, slowly contracting as surrounding space expands beyond them. Over even longer intervals, these structures stabilize into isolated islands of matter in an otherwise expanding void. Despite this long-term trend toward isolation, the smaller-scale processes within gravitationally bound systems remain active. Stars continue orbiting the remnants of their galaxies. Stellar remnants occasionally interact, merging or scattering through gravitational encounters. Rogue planets and brown dwarfs drift through the dark, illuminated only by distant starlight or by the faint thermal glow retained in their interiors. At the quantum level, spacetime remains dynamic. Virtual particles arise and vanish within fractions of a second, contributing to the vacuum energy that drives cosmic expansion. Although invisible in everyday life, these quantum fluctuations shape phenomena as large as black hole evaporation and as subtle as the slight variations detected in precision experiments. Across this immense landscape, the universe displays a consistent theme: transformation driven by time, governed by fundamental laws, and expressed through patterns that span all scales. From the interior of atoms to the formation of galaxy clusters, each event follows principles rooted in symmetry, energy distribution, and gravitational interaction. These relationships tie together the history of the cosmos, creating a coherent narrative emerging from the interplay between order and change. Even the smallest particles play essential roles. Protons, for example, are predicted by some theories to decay over extremely long timescales, although this has never been observed. If proton decay occurs, it would gradually transform matter into lighter particles, changing the composition of the universe during exceedingly distant epochs. Electrons and neutrinos may remain among the final survivors of physical processes, drifting through expanding space long after stars and galaxies have faded. Yet despite the eventual cooling and dispersal predicted for the far future, the present universe remains filled with activity. Star formation continues, galaxies interact, and cosmic structures grow. Observations across all wavelengths reveal intricate details about these processes, enabling scientists to reconstruct the past and predict the future with increasing accuracy. Each discovery adds depth to our understanding of how the universe evolves, demonstrating the profound connection between small-scale phenomena and the largest structures known. As cosmic time advances into regions almost unimaginable on human scales, slow but persistent physical processes begin to dominate the universe's long-term development. Each mechanism, though subtle in its moment-to-moment effect, shapes the distant future in ways that reveal the deep interconnection between matter, energy, and space-time. In gravitationally bound systems, such as galaxies and clusters, stars continue their orbital motions around common centers of mass. Over immense periods, Gravitational encounters between stars cause gradual redistribution of energy. Some stars gain velocity, drifting into wider orbits or even being ejected from their galaxies into intergalactic space. Others lose energy and migrate inward, crowding the central regions. This process, known as dynamical relaxation, slowly reshapes the internal structure of stellar systems. Globular clusters, dense, ancient spheres of stars, experience these effects particularly strongly. Their cores can undergo collapse as stars migrate inward, increasing central density until interactions form tight binary systems that release energy back into the cluster. This cycle of collapse and re-expansion can repeat many times over billions of years, producing shifts in structure that preserve the integrity of the cluster while altering the distribution of its stars. Meanwhile, galaxies traversing the intracluster medium experience gravitational tides from nearby systems. Over time, repeated interactions gradually strip stars from their outer regions, forming diffuse intracluster stellar populations. These wandering stars no longer belong to any one galaxy, but drift freely within the cluster, contributing to faint stellar halos that extend far beyond visible galactic boundaries. On the scale of galaxy clusters themselves, mass continues to accumulate at their centers. Dark matter halos deepen as more matter falls inward, while black holes formed from ancient mergers grow through occasional accretion. Although the rate of growth diminishes as the universe expands, the gravitational framework remains stable within the boundaries of the cluster. Outside these regions, however, cosmic expansion accelerates. Distances between unbound galaxies increase at growing rates, stretching spacetime and diluting matter. Radiation becomes increasingly redshifted, its wavelengths stretched until they fade beyond detectability. The cosmic microwave background, once a clear map of the early universe, gradually weakens into an almost uniform signal indistinguishable from the vacuum. Even within the solar system, slow transformations accumulate. Planetary orbits evolve due to gravitational interactions, tidal effects, and mass loss from the Sun as it converts hydrogen into helium. Over billions of years, small resonances between planets can slightly alter orbital eccentricities and inclinations. Asteroids and comets experience gentle perturbations from passing stars or interstellar clouds, altering their trajectories on timescales far longer than recorded human history. Far from stars, the interstellar medium remains dynamic. Dust grains collide and fragment, molecules form and break apart, and cosmic rays propagate across space. Gravitational waves from distant mergers cross vast distances, carrying information about events that occurred millions or even billions of years earlier. These ripples subtly stretch and compress space-time as they pass, invisible to human senses but measurable with precise instruments. In dense molecular clouds, chemistry continues to evolve. Complex organic molecules can form through surface reactions on dust grains or through photochemical processes triggered by ultraviolet radiation. These molecules may later seed, forming planetary systems, contributing to the initial chemical inventories of young worlds. Although chemical activity slows as gas becomes more diffuse, pockets of denser material persist, providing environments where molecular processes remain active. Closer to stars, exoplanet atmospheres undergo long-term evolution driven by stellar luminosity changes, impacts, geological cycles, and magnetic interactions. On worlds with volatile cycles, Atmospheric composition can shift significantly as oceans evaporate, freeze, or react with surface minerals. Gas giants experience internal differentiation as heavier elements sink toward their cores, while lighter components migrate outward. Such processes transform a planet's appearance over time, gradually altering cloud patterns, temperature gradients, and atmospheric chemistry. Brown dwarfs. Objects too massive to be planets, yet not massive enough to sustain hydrogen fusion, cool steadily. Their infrared glow diminishes, but they maintain complex atmospheric structures shaped by dust grains, metallic condensation layers, and turbulent flows. These substellar objects populate interstellar space in vast numbers, acting as quiet markers of star formation history. As cosmic time extends further, gravitational interactions begin to dominate over processes that once drove large-scale structure formation. Within gravitationally bound clusters, galaxies merge occasionally, but the pace of interaction slows dramatically as ambient gas becomes scarce and velocities between objects stabilize. Without continuous infall of fresh material from large-scale filaments, now stretched beyond the cosmic horizon, these clusters become essentially isolated islands of matter within an ever-expanding void. At extremely distant epochs, when most stars have exhausted their fuel, stellar remnants become the primary constituents of galaxies. White dwarfs, neutron stars, and black holes orbit one another in complex arrangements influenced by gravitational encounters. Occasionally, binary systems form between remnants, leading to mergers that produce brief but powerful bursts of gravitational waves and electromagnetic energy. These rare events inject new motion into otherwise quiet regions of space. Even after the visible components of galaxies fade, dark matter remains, preserving the gravitational structure of each bound system. Dark matter halos continue to shape the orbits of stellar remnants and influence the movement of any surviving planets or rogue bodies. Their invisible presence endures long beyond the luminous era of the universe. At the boundary of theoretical physics, models explore profound possibilities regarding the fate of matter and energy. If protons eventually decay, as some grand unified theories suggest, all baryonic matter would gradually transform into lighter particles. Over unimaginable timescales, this would dissolve the last structures made of ordinary matter, leaving behind only black holes and increasingly sparse particles distributed across space. Eventually, even black holes, once the most enduring of cosmic structures, would slowly lose mass through Hawking radiation. Small black holes would evaporate first, releasing bursts of energy in their final moments. Larger ones would take vastly longer to vanish, but even they are predicted to dissipate entirely after timescales of 10 to the power of 100 years or more. The end result is a universe composed primarily of low-energy photons, neutrinos, and extremely diluted particles drifting across an expanding cosmic horizon. Despite the dramatic scale of these transformations, each step follows from the same principles that govern the cosmos today. Gravity, quantum mechanics, thermodynamics, and the behavior of fundamental particles shape the universe across all eras, from its earliest moments to distant futures. The coherence of these laws provides continuity across time, linking all stages of cosmic evolution into a single, connected narrative. As cosmic time stretches further into remote epochs, the interplay between fundamental particles and the expanding fabric of spacetime begins to dominate the universe's physical behavior. Even seemingly insignificant interactions, particle collisions in near-empty regions, quantum fluctuations in vast voids, or rare encounters between stellar remnants, accumulate into outcomes that define entire eras. At the scale of galaxies, the slow redistribution of energy continues over trillions of years. Stellar remnants drift into new orbits as gravitational encounters subtly alter their trajectories. Some remnants escape their host galaxies entirely, becoming intergalactic wanderers moving through regions that grow increasingly sparse as cosmic expansion accelerates. These isolated objects, though rare in the current universe, become far more common in the distant future as gravitational interactions gradually eject stars and remnants from clusters. Meanwhile, the nature of matter itself undergoes theoretical long-term changes. Although protons are extremely stable on human timescales, some grand unified theories predict they may decay after periods far exceeding the current age of the universe. If proton decay occurs, atomic matter would slowly transform into lighter particles such as positrons, pions, and neutrinos, gradually reducing the population of baryonic matter. The rate of this transformation would be incredibly slow, but over timescales of tens of billions of trillions of years, it would reshape the universe entirely. In galactic remnants where black holes remain dominant, gravitational interactions continue to sculpt the local environment. Black holes at various mass scales, stellar, intermediate, and supermassive, may form binary systems or occasionally approach one another closely enough to interact. These encounters can eject one black hole from the system entirely while causing the other to settle into a more stable orbit. In rare instances, black holes can merge, releasing gravitational waves that ripple outward across an ever-expanding spacetime. As the supply of matter available for accretion dwindles, black holes grow increasingly quiet. Without streams of gas feeding their accretion disks, their X-ray and gamma-ray emissions fade. Supermassive black holes that once shaped the evolution of entire galaxies become dark, nearly undetectable gravitational anchors surrounded by sparse populations of stellar remnants and cold debris. Far beyond these structures, in the increasingly empty voids between gravitationally bound systems, the expansion of the universe becomes the dominant influence. Space stretches faster than light can traverse it, causing distant regions to slip beyond each other's cosmological horizons. What was once a single, observable universe becomes fragmented into isolated sectors, each unable to exchange information with the others. Yet even within isolated gravitational islands, smaller-scale processes unfold. White dwarfs cool toward black dwarf status, losing the last traces of thermal radiation. Neutron stars gradually slow their rotation until their magnetic emissions fade. Brown dwarfs dim as their residual warmth radiates into the thinning interstellar medium. Gravitational interactions still occur on small scales. Binary remnants merge over immense periods, producing short flashes of high-energy radiation that punctuate increasingly quiet cosmic landscapes. These events, though rare, contribute to the slow redistribution of mass and energy. At the same time, subtle quantum phenomena remain active throughout space. Virtual particles emerge and annihilate in fractions of a second, influencing the vacuum energy that drives cosmic expansion. In the vicinity of black holes, quantum effects manifest as Hawking radiation, slowly reducing the mass of these compact objects. For stellar mass black holes, This process is extraordinarily slow, but for smaller black holes or hypothetical primordial black holes, evaporation occurs more rapidly, producing bursts of energetic particles in their final moments. In the environment surrounding long-cooled stars and black dwarfs, gravitational capture of passing particles becomes less likely as matter becomes increasingly diluted. Over extended timescales, the distribution of matter shifts toward uniformity at small scales, while large-scale structures remain governed by the invisible frameworks of dark matter halos. At the largest scales, dark matter itself may undergo transformations. Some theoretical models propose decay processes for dark matter particles, potentially releasing energy or lighter particles after extraordinary time spans. If such decay occurs, the gravitational landscape of the universe would shift gradually as halos lose mass, altering the dynamics of bound systems. Clusters could become less dense, and galaxies within them might drift into wider orbits. Quantum tunneling, a process where particles pass through energy barriers they cannot classically overcome, may influence the stability of matter in extreme future epochs. Electrons bound to black dwarf remnants might slowly tunnel into their nuclei, triggering collapse or transformation into neutron-rich matter. Such processes would occur on timescales so large they are nearly impossible to conceptualize, yet they highlight the persistent influence of quantum mechanics even in an increasingly cold universe. In regions where small pockets of gas remain, gravitational collapse could still occur, but the likelihood decreases as gas becomes more diffuse. Star formation, once widespread and vigorous, eventually ceases entirely. Without new stars, galaxies lose the bright structures that defined earlier cosmic eras. What remains are faint collections of remnants, still following predictable gravitational paths, but no longer illuminated by ongoing nuclear fusion. Across these vast stretches of time, the cosmic microwave background continues to cool, its wavelength stretching until it becomes undetectable. Neutrinos and extremely low-energy photons become the dominant relics of ancient cosmic radiation. The universe transitions from one dominated by luminous structures to one defined by sparse, faint interactions among remnants of remnants. Yet even as the universe becomes darker and colder, the principles that governed its early growth remain in effect. Gravity still binds matter into clusters. Quantum mechanics still governs particle behavior. Thermodynamics still dictates the flow of energy. The continuity of these laws connects the earliest moments of the cosmos to its most distant future, unifying all epochs into a coherent physical narrative. The transformation of the universe does not occur through abrupt shifts, but through slow, cumulative processes. A star collapsing into a white dwarf, a black hole gradually evaporating, a galaxy drifting beyond the cosmological horizon. Each event is part of the same unfolding structure shaped by fundamental interactions. Matter that once formed planets, stars, and living organisms becomes redistributed into simpler particles. The structures that once dominated the cosmos, spiral arms, glowing nebulae, dense clusters, fade as energy dissipates. Over spans that dwarf the lifetimes of galaxies, the universe approaches a state in which only a few long-lived processes continue to operate. Across these distant epochs, the connection between the smallest and largest scales becomes more apparent. The decay of fundamental particles influences the fate of galactic structures. The expansion of spacetime determines whether remnants remain gravitationally bound. Quantum processes affect the stability of matter in cold, sparse environments. Every aspect of cosmic evolution remains linked, reflecting the underlying unity of physical law. As the universe advances deeper into its distant epochs, the distribution of energy becomes increasingly uneven. Regions that once hosted active star formation grow silent, while pockets of matter continue to evolve under gravity's persistent influence. The interplay between thermal processes, quantum effects, and space-time expansion becomes the defining framework of cosmic behavior. In galactic remnants, the patterns of motion reflect a long history of gravitational exchange. Even without luminous stars, stellar remnants continue orbiting the dense centers of their former galaxies. Their motions trace the enduring influence of dark matter halos, which maintain their gravitational imprint long after the visible components have vanished. These halos stabilize the orbits of neutron stars, white dwarfs, black dwarfs, and black holes, forming a faint skeletal map of the galaxies that once glowed brightly across the universe. Among these remnants, occasional collisions still occur. White dwarfs drifting into binary systems may accumulate material from companion remnants, reaching critical mass limits that cause collapse into neutron stars or triggering thermonuclear outbursts that disperse remaining matter. Neutron stars that merge generate brief but powerful emissions of gamma rays and gravitational waves. Although rare in the late universe, such events punctuate otherwise quiet cosmic backgrounds with isolated instances of extreme energy release. In isolated pockets where gas remains gravitationally bound, molecular processes slow to near standstill as temperatures drop and particle interactions become infrequent. Remaining molecules freeze onto dust grains or become trapped in gravitationally stable orbits around stellar remnants. Without the ultraviolet radiation of active stars, chemical reactions that depend on photonic energy proceed more slowly or cease entirely. Over extensive periods, complex molecules may break down into simpler components through cosmic rays or quantum tunneling. In some models, black dwarf stars, former white dwarfs that have cooled into darkness, may eventually undergo rare quantum transitions. Over immensely long timescales, carbon nuclei inside a black dwarf could fuse through tunneling, slowly transforming the remnant into heavier elements. This process, predicted theoretically, would proceed extraordinarily slowly but demonstrates how quantum effects can dominate the far future of cosmic evolution. Beyond gravitationally bound regions, the universe's expansion continues to stretch spacetime. Photons that once traveled freely between clusters now lose energy as their wavelengths lengthen. Even high-energy radiation from neutron star mergers or evaporating black holes becomes gradually redshifted until it blends into the increasingly homogeneous background. The detectable universe shrinks as distant regions accelerate away faster than light can bridge the growing gaps. Black holes, once dominant engines of energetic output, eventually exhaust their ability to accrete matter. Their surroundings become increasingly devoid of material. Without accretion disks or infalling gas, black holes grow silent. Hawking radiation becomes their only mechanism of energy release, an almost imperceptible quantum glow that carries mass away bit by bit. For supermassive black holes, the evaporation process takes incomprehensibly long, but the outcome is inevitable in a universe governed by quantum physics. As black holes evaporate, they pass through stages of increasing temperature and radiation output. Their mass loss accelerates near the end, producing intense bursts of particles before they vanish entirely. These final events mark some of the last significant energy releases in a universe transitioning toward extreme thermodynamic equilibrium. In the long-term thermodynamic picture, the universe moves toward increasing entropy. Structures once capable of storing and transferring energy dissolve or cool. The density of matter and radiation becomes more uniform within each gravitationally isolated region. Without significant energy gradients, large-scale physical processes slow dramatically. Yet, even in this state, quantum fluctuations persist everywhere in space-time, preventing the universe from becoming entirely static. Across trillions of years, even the frameworks of galaxies may shift subtly as dark matter evolves. If dark matter particles undergo decay or annihilation, their influence on gravitational potentials will slowly diminish. As halos lose mass, the orbits of stellar remnants may expand, and gravitational bindings may weaken. Structures that persisted for unimaginable lengths of time could eventually disperse into sparser configurations. Despite this gradual dispersal, continuity remains. The laws governing particle interactions, spacetime geometry, and energy distribution maintain coherence across epochs. Even as the composition of the universe shifts toward low-energy radiation and sparse particles, the underlying principles shaping these transformations remain the same ones that guided the formation of galaxies, stars, and planets. Within isolated remnants of galactic clusters, interactions proceed on scales that defy ordinary intuition. Two black dwarfs separated by light years may slowly drift toward each other due to minuscule gravitational influences or perturbations accumulated over trillions of years. Their eventual merger, though extremely rare, would represent a final echo of stellar evolution long after ordinary stars had disappeared. These events are sparse, but serve as reminders that gravitational dynamics persist even in an aging cosmos. Meanwhile, free electrons and neutrinos continue to populate the universe. Neutrinos, barely interacting with matter, pass through vast distances unimpeded. Their distribution remains almost uniform as the universe expands, gradually losing energy but never ceasing entirely. Electrons, protons, if stable, and other particles become increasingly rarefied as expansion continues. Over such vast timescales, quantum statistical behavior becomes increasingly important. Particles follow probability distributions that govern their interactions and motions in the near-absolute zero environment of distant cosmic futures. The interplay between thermodynamics and quantum fields defines the ultimate fate of matter, dictating whether structures dissolve, collapse further, or remain stable indefinitely. The universe becomes a place dominated by remnants, isolated black holes slowly evaporating, neutron stars maintaining their dense structures, and dispersed clouds of particles drifting across space. While the luminous, structured universe fades, the underlying physics remains active, subtle but persistent, governing the motions of particles and the curvature of spacetime. Yet through all changes, the narrative remains coherent, a transition from a hot, dense early universe to one filled with stars and galaxies, followed by gradual cooling, expansion, and the dissolution of large-scale structures. Each phase follows naturally from the previous one, forming a continuous chain of transformations that reflect the interplay of fundamental forces. As this progression continues, the universe enters into eras where interactions become increasingly rare but not non-existent. Quantum tunneling processes, gravitational captures, particle annihilations, and black hole evaporation ensure the cosmos retains dynamic behavior even in its most remote future. As the universe advances into its most remote ages, the physical landscape becomes dominated by the faintest remnants of structures that once defined the cosmos. The vast star-forming regions, once illuminated by clusters of bright young stars, no longer exist. The brilliant galaxies that trace the cosmic web have faded into collections of cold remnants, each following predictable gravitational paths in the dark. Yet, even in this extreme future, the universe remains governed by the same principles that shaped its earliest moments. Within gravitationally bound systems, the last black holes continue their slow evaporation through quantum processes. Their mass decreases at an almost imperceptible rate, but as they shrink, the energy they emit increases. This final radiative burst marks the end of objects that once anchored entire galaxies. When the last black hole evaporates, a transformation occurs. For the first time since the universe's beginning, no region of space will contain an object capable of gravitational collapse on large scales. After these events, the universe enters an era defined by cold, sparse particles. Photons stretch to wavelengths beyond any meaningful detection, carrying only faint traces of energy from earlier epochs. Neutrinos drift across expanding distances, their interactions nearly negligible. Electrons and any remaining stable baryons exist at such low densities that collisions between them become extremely rare. The cosmos becomes a nearly homogeneous expanse with only slight variations in particle distribution. Quantum mechanics continues to govern the behavior of the remaining particles. In this deep future, the distinction between classical and quantum processes becomes increasingly blurred, as interactions rely on probability rather than thermal kinetic energy. Tunneling events, once insignificant on cosmic scales, become the primary drivers of rare transformations. In a universe cooled close to absolute zero, even the smallest quantum fluctuations influence the fate of matter. Spacetime, still expanding, becomes the dominant arena. Distances grow so vast that regions which once belonged to the same supercluster no longer share causal contact. Horizons form around isolated gravitational pockets, enclosing the last regions where particles remain bound together. Beyond these horizons, expansion accelerates space into further isolation, effectively fragmenting the cosmos into independent sectors. Even as structure dissipates, the fabric of space-time remains imprinted with the memory of its long evolution. Gravitational potentials, though faint, persist as subtle ripples shaped by the distribution of particles. These lingering patterns, stretched by expansion, represent the fading signatures of galaxies, clusters, and black holes that once defined the universe's architecture. Across unimaginable lengths of time, the cosmos approaches a state of maximum entropy. Not a static, featureless void, but a configuration where no large-scale gradients persist. Energy becomes evenly dispersed within each isolated region. Processes that once built stars, drove galaxies, and shaped clusters no longer occur. The universe transitions from a dynamic interplay of forces into a quiet, balanced configuration governed by the rules of statistical physics. And yet, even in this distant age, the story retains coherence. From the earliest quantum fluctuations to the formation of galaxies, From the birth of stars to the creation of planets, from the emergence of complex structures to their eventual dissolution, every stage reflects the continuity of natural law. The universe evolves not through sudden shifts, but through an unbroken sequence of changes driven by fundamental interactions. This long arc, from a hot, dense beginning to a cold, diffuse future, reveals the strength of the principles underlying cosmic history. Gravity, thermodynamics, quantum mechanics, and relativity shape all scales, linking the smallest particles with the largest clusters. Their combined influence defines the universe's past, present, and eventual fate. Though the luminous epoch ends, the narrative of the cosmos remains intact, a progression defined by transformation, governed by symmetry, and guided by laws that operate with the same consistency across all eras. The universe, in all its phases, remains a testament to the interconnectedness of matter, energy, and spacetime. Across billions of years, the universe unfolded from a simple beginning into a tapestry of galaxies, stars, planets, and structures of remarkable complexity. It passed through eras of formation, growth, interaction, and transformation, eventually transitioning into a realm shaped by remnants and governed by slow, persistent processes. Yet, through every stage, the same physical laws guided its evolution. The story never belonged to one era alone. It stretches from the first flickers of energy to the distant ages where only faint particles drift through expanding space. It is a single, continuous history, vast, intricate, and unified by the principles that shaped everything from atoms to galaxies. And with this final section, the narrative reaches its closing moment. A completed journey through the lifespan of the cosmos, written in the same quiet, steady rhythm that defines the universe itself.